Okay, for section 3, we're going to really get into the machine learning side of this. Now, there's a little bit of data processing we have to finish, mostly just splitting the data into test and training sets. We'll do that in a little while. We'll also talk a little bit about model selection and how to import a model, how to set the model object, how to fit it, how to test it, how to see its performance, all of that. We'll do that all right here. So to start off with, what we started with was we had a heat capacity data frame that contained all of the chemical formula and all of their respective properties. We took that data frame and we took the chemical formula and we split them up into features. We called that data frame features, and we used a function that I made for you guys there. And then we took the properties, and we put that in a series for our targets. So maybe this should say target series instead of data frame there, but it's fine. So what we're going to do now is we're going to take that data, and if you remember, kind of had it formatted like this, and we're going to split it into training and test sets. So I'm going to use a red line to kind of indicate how we're going to cut that data. Now, for us, we're not going to split it. If this is our index starting at 1 going to 277, we're not going to split it 1 to 150 and then 151 to 277. We're going to randomly sample. So instead of this red line, maybe everything in the red box will be taken as testing, and everything not in red boxes will be for training. But we'll do a bunch of little samplings of the data set. So red would be for testing. And we'll split that up. So there's a really, really easy way to do this, and it's built into the sklearn library in the model selection package. So I call this one a library because it's got a ton of, they're probably all libraries, but this one's got a ton of little things we're going to be calling from like little internal packages. So in model selection, so from sklearn.model selection, we're going to import train test split. So that's going to do what we just did over here on this paint. It's going to take our data and it's going to split it, and you'll have equivalent splits over here. These should all match, but forgive me for my paint drawing. So these will all match up. The formula feature with their respective properties will always be put into the same set. So here, what this code does is I'm saying I want an X train. So this is my feature matrix, or my feature data frame. So X train, X test. So that would be this left side here. Maybe X train is the red, X test is not in the red box. And then Y train, Y test. So again, Y train would be in a red box and Y test not in a red box, or something like that. And so we're going to say set these 4 variables to the value of this function. So this function is going to have 4 separate values at outputs, and they're going to go to these 4 variables. What this function does is it reads in a features and a targets data frame. And then it splits those guys using the same split on both of them so that we have a test size of 1/3 of the data. And then we can choose the random state so that the split's always the same, so things are recreatable. So in this case I've said random state equals 1. So we look, and it has split our data into 184 and 92. Okay, so then, kind of going back to this picture one more time, we would say that red would represent 180, or red would represent 66%, and then black might represent the other 33%. So we can write right in here. This would be our train, and this would be our test. And similarly, we'd have these same looking guys for our label. Hopefully, you get the idea here. Yeah, something like that. Okay, so we've essentially made this split with this line of code right here. Okay, now we want to create a model and be able to verify its performance. So to do this, I'm going to use a random forest regressor. So this is a regression because we have numerical values here. If you're trying to classify whether or not this is a solid or a liquid or something, that would be a classification. So here we're going to do a random forest regression. So I'm going to, from scikit-learn, so sklearn ensemble package, import the random forest regressor. So I'm going to say RF, so I'm setting a specific instance of this object. So I want my own version of this. So random forest, and I want my version called RF to have 150 trees. They can go to a max depth of 40, and I'm saying you have to have at least, you have to have at least 1 sample in each leaf. So you can have a little bit more, but you have to have at least 1. And so then once I've created my instance of that, I can train my model, or I can fit the data to the model, or fit the model to the data. So this is like the physical building of a decision tree. 150 times would happen here. And so once I've done that, it kind of gives me, okay, this is, for RF, we fit it using these parameters, because RF was defined to have, 150 estimators, depth of 40. And then all of these other values were just default values that were given to it. So it said, we used the random forest algorithm, we made one for you called RF with these specific parameters, and we fit it using the training data for the features and the training data for the properties of the target. Now that we have that, we can use this trained model. So RF has now been fitted to the data. We can use this model to do a prediction. So I do rf.predict, and then I put in my X features, and it's going to return a prediction of what it thinks the target should be. So if we go back over here, I trained a model on this section, and then I took that trained model, I put this test value into it, and it's thinking, okay, given the performance of the training set, I expect y values, so this set of values here, to look like this, you know. And it's going to predict some sort of output. So it's going to give me a test, or we'll call it, we had y test up here, so we had y test, so we'll call this y predict, or y predicted, okay? So that's what's going on here. So if we look back, we have our training data to fit to the model. Then using that fit model, we're predicting our y values. And then we can also ask it, okay, given x values, so given my features, and given what the real values are, what do you think, what's the score based off of your predictions? So the first thing it prints is a score. And this is a coefficient of determination. So that's pretty good. That means it fits really well. Most of the variance in the data is really well described by the model. So then if we want to really visualize this, we can plot. So we're going to plot the actual values, so y test, so the real heat capacities, versus the predicted heat capacities given that formula feature, or given the formula features we fed it. And this, I think, is like kind of the summary and the real idea. All of that culminates to this right here, this image. We can see our predicted heat capacity on the y-axis and our actual heat capacity on the x-axis. If I line up on this line, that means my predictions perfectly matched the actual values. So that would be an incredible model, and we don't expect to be incredible, but we can see that we're really quite good. So for almost every value, we're almost right on. And you know, there's a couple. Maybe this is like at 175 and this is 150. So that's off by like 25 joules per mole Kelvin, and that's, I would say that's significant. Like, you know, you've got this one that's maybe like 60 and 25, so that's even more significant. That's quite a bit of, you know, quite a percent change from the real value. But overall, the model performs quite well at identifying what a heat capacity should be, given a bunch of elemental information. And this is the heat capacity of the combined system, and that right there isn't unintuitive. The Newman-Kopp predictions essentially do just that. They predict heat capacity based off of the elemental heat capacities added together. And so it's really good to see that our model can perform, you know, at least in a similar way to some other sort of standard that we've, as material scientists, have accepted. So that's really good. That's awesome. That shows that machine learning was able to predict quite well what we want. So in summary, I guess, and this is kind of fun to talk about, we looked at how to import the Python packages, how to install Python, just grabbing the heat capacity data and visualizing it. We talked about like transforming the data to be normalized, like the log transformation or square root transformation. And it's possible that that would have improved performance here. Also, we created features and feature vectors, and we split them up into training and test sets. It's possible that we could, if we made a smaller test set and a larger training set, that performance would be a little bit better because the model sees more instances of heat capacity. Or we could look at other things like after doing the training and test set, swapping them so that the test set becomes the training set, or doing like a full cross-validation. So there's lots of ways to get more data here and have a better understanding of how our model works, but for now this is a good introduction. We grabbed a random forest model. There's a lot of different ways we could do this. We could have used support vector machines. We could have used a linear regression. Heck, I don't know if it's a great idea, but we could have thrown it through a neural network. So there's a lot of machine learning algorithms you can choose for this type of problem, and that's why this is a really good problem to look at. It's a really good introduction. And finally, we just briefly looked at the performance. There's a lot of other metrics we could have used instead of just an R-squared score. We could have done like a, mean squared error or a average percent error, that sort of thing. But as it is, I think this visual metric is one of the best indicators of the performance of our model. And it's very quick, very easy. You can see immediately, oh yeah, it looks like it's performing well. It looks like it's getting close overall. So that should be it for section 3. Hopefully you have an idea now. Hopefully you have an idea what's going to be going on in the workshop. I'm going to talk about most of section 2 and 3 in more detail with a different data set. And we're going to go into a lot more exploration of model parameters, what works there. We'll talk about, are there different algorithms that perform better than this random forest I tested? And we'll look at, what's the effect of normalizing our data, or what's the effect of eliminating some of the extra features that don't do much. We'll talk about all of that later in the workshop. For now, I hope this just gives you the baseline fundamental understanding to come prepared to learn more. Thank you.